Yes, from Trace, welcome back for our chemistry class. And today we are going to look at the physical properties of alkanes. So, physical properties, that is the subtopic. And the objective is to describe the physical properties and explain them. We should be able to explain the physical properties of alkanes using chemistry concepts. Now, what are these physical properties? I have a table here, and in this table, I have summarized the physical properties of alkanes. I have listed the alkanes, their molecular formula, their molecular formulae, and we are going to calculate their relative formula mass. And then we have the melting points as a physical property, boiling points as another physical property, physical states also a physical property, and then density. We will also talk about their solubilities. Now, this table is going to form the foundation of our studies today. And the first thing we are going to look at is the relative formula mass of these alkanes. So, how do we calculate the relative formula mass? Remember, these are molecules. So, the relative formula mass of alkanes, like for example, if you want, you know that carbon is 12, hydrogen is 1. That is something you know. So when we're given CH4 and you want the relative formula mass, carbon is 12 plus hydrogen is 4. 1 times 4. This one will give us 16. When we come to ethane, carbon is 12 times 2 plus 1 times 6. So this one is 24 plus 6 is 30. Moving down to propane, we will have 12 times 3 plus 8. This is 20, 36. 36 plus 8 is 44. Then when we come to C4, H10, it will be 12 times 4, which is 48, plus 10, 58. So from here, we can see that as the number of carbon atoms increases, the relative formula mass also increases. You can call it relative formula mass, you can call it relative molecular mass, you can call it molecular mass. At times we will talk about molecular size, the size of the molecules. So as the number of carbon atoms increases, the relative formula mass will also increase. That is one thing that we must notice in the table. So the relative formula mass of alkanes increases with increase in the number of carbon atoms. That one we have proved. Then the second thing is the structure of alkanes. We have learned about structural bonding, and we have seen that covalent bonding can result into either simple molecular structures or giant atomic structures. Now, if here we have alkanes, what type of structure do alkanes have? alkanes have simple molecular structures. And we know that in simple molecular structures, molecules are held first. Atoms are bonded by strong covalent bonds to form discrete molecules, to form independent molecules. These stable molecules are in turn held by weak intermolecular forces of attraction. An example of a weak intermolecular forces of attraction is the van der Waals forces. So alkanes consist of molecules which are held by weak van der Waals forces or weak intermolecular forces. But are these forces the same in strength? That is now what we must explain. Now, intermolecular forces of attraction are not similar in strength. The van der Waals forces are not similar in strength, but the strength of the van der Waals forces depends on the size of the molecules. The longer the size, the longer the carbon chain, the stronger the intermolecular forces of attraction. If you have an alkane of 2 carbon atoms, like this, now we have intermolecular forces of attraction. These forces will be much weaker compared to where you have a long chain. So where we have a long chain, the intermolecular forces of attraction will be stronger. So that's why we are saying in this point number 4 that the strength of the intermolecular forces of attraction, an example is van der Waals forces, the strength increases with increase in the molecular masses or increase in the molecular size. Hence, alkanes with longer chains of carbon have stronger intermolecular forces of attraction than alkanes with shorter carbon chains. That one is very, very clear that van der Waals forces are stronger in octane but weaker in methane. Stronger in pentane but weaker in heptane. Stronger in heptane but weaker in pentane. That one is a very, very important point because it will explain most of the variations in the physical properties of alkanes. Now, let us come back to the table and talk about melting and boiling points. If you look at this table, there is a clear general trend that as you move downwards, as the number of carbon atoms increases, the melting and boiling points of alkanes also increases. Therefore, for example, pentane has a higher melting and boiling point than ethane. Decane has a higher melting and boiling point than the rest in this table. So, why is it that all these substances have simple molecular structures, but they have different melting and boiling points? The reason is that when you are melting or boiling a substance, the heat energy supplied is normally used to break the intermolecular forces of attraction. When melting and boiling a substance, the heat energy supply must be enough to overcome the intermolecular forces of attraction. We have said that those alkanes with shorter chains of carbon atoms have weaker intermolecular forces of attraction, which require little amount of heat energy to break. While those alkanes with longer carbon chains have stronger intermolecular forces of attraction, which require large quantities of heat energy to break. That's why when you go to point number 5, the melting and boiling point increase as the carbon chain increases. This is because the increase in the strength of the van der Waals forces or intermolecular forces as the carbon chain increases. So as the carbon chain increases, the van der Waals forces become stronger and more energy, heat energy will be required to break them. Let us stop there and then connect in the second part of this video.